Hello everyone. Today I am going to present my lecture on shear strength of soil. I am Ajit Kumar Paria, Assistant Professor of Department of Civil Engineering, Haldia Institute of Technology. So shear strength means the strength, the maximum strength given by the soil against shear failure. Now what is shear? When upcoming load, the normal load is acting on the soil mass, that time which is acting vertical, obviously in the downward direction, that time the underlying particles that are sliding or moving in the lateral direction, this movement is called as the shear. So before shear failure, the maximum capacity, the maximum strength given by the soil will be called as the shear strength. So it is a function of stresses applied on the soil mass as well as the manner in which the stresses are applied. This knowledge of shear strength is very much essential in determining the bearing capacity of soil, the lateral pressure exerted on the retaining wall, and the stability of slope. First of all, we have to understand that what is Mohr circle of stress. Generally, for the soil testing, we prefer cylindrical soil samples. On these cylindrical soil samples, when it is being stressed under the stress condition, three kind of principal stress will act in three principal planes. Now what are principal planes? Principal plane means along a particle infinite number of planes may be drawn, out of which we are considering three principal planes which are perpendicular to each other. So along these principal planes, three stress will act, those will be called principal stress. The major principal stress will be denoted by sigma 1, the minor principal stress will be denoted by sigma 3, and the intermediate one will be denoted by sigma 2. So considering these stresses, we have to plot it graphically to represent the stress, which is called as the Mohr circle. This is a soil sample on which the stress are acting. On the right hand side figure you can see the sigma 1, the major principal stress acting in the vertical direction, that is the major principal stress, and in the lateral direction minor principal stress sigma 3 is acting. So this sigma 1 and sigma 3, major principal stress, minor principal stress, are being plotted on this graph. Here you can see that is the sigma 1 the major principal stress, and this is the sigma 3 minor principal stress. Considering these 2 points as the diameter, take a center and draw the circle. This circle will be called as the Morse circle. So any point on this circle will give you the normal stress sigma and the shear stress tau. We have taken sigma on the along x-axis and tau along y-axis. Now any point sigma tau, if you join this point with the minor principal stress point, that is sigma 3, that is making an angle theta. So obviously with the center it will make 2 theta angle. Here it is being clearly depicted. The left hand side figure, the sample is under stress, and on the right hand side figure it is depicting how the radius and the center of the circle, the Morse circle, that have been found out. Radius of the Morse circle is being given by sigma 1 minus sigma 3 by 2, and the distance of center from the origin, that is your sigma 1 plus sigma 3 by 2. So from this Morse circle diagram, the normal stress given by sigma, that is equal to sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos 2 theta. From graphical analysis we can find out this one, and shear stress tau given by sigma 1 minus sigma 3 by 2 sin 2 theta. From previous diagram that have been found out, the plane inclined at an angle 45 degree, the horizontal has acting the maximum shear stress when theta become 45 degree. The maximum shear stress given by sigma 1 minus sigma 3 by 2, and the normal stress given by sigma 1 plus sigma 3 by 2. Now comes as Moore-Coulomb-Fourier criteria. Generally, when we take cylindrical soil sample and on which the stress is applied, during that time, before failure, the failure planes are coming on the soil sample. So from this plane, failure planes, we have to find out the maximum shear stress that is acting on the sample, or the ratio of shear stress to normal stress when it will be maximum. So this is a typical graphical representation from the available data or the observed data from on a soil sample, where this inclined line representing the failure plane. Now how it is coming? On the below figure it is being depicted that from a triaxial test that we will discuss in the later on slides. On the 3 sample we get sigma minus sigma 3 value if it is being plotted in this way. So a typical tangent or common tangent that have been drawn, it is touching all the circles and it is meeting at a certain point along y-axis, which is representing shear stress tau. So the inclination of this line with horizontal, that is your phi, and the intercept along y-axis, that is given by c. So the equation of this line now become S is equal to c plus sigma tan phi. That is the equation of shear strength of soil. C plus sigma tan phi. C is the cohesion, phi is this angle of inclination with horizontal, that is also called as internal frictional angle of soil, and sigma, that is the normal stress acting on the soil mass. Now for this typical circle, Moore circle, that is the failure envelope, the inclined line, which have C intercept along y-axis, that is the cohesion, and if we extend it in the negative x-axis, the distance of this point when it is meeting the x-axis is C cot phi. So from this diagram, now it is being analyzed that the failure, Moore Coulomb failure envelope or criterion, that can be written in this form: the tau f is equal to C plus sigma f tan phi. Tau f is the shear strength or the maximum shear stress on the failure plane. C is the apparent cohesion. You know, cohesion is the particle to particle interaction force. Sigma f is the maximum normal stress acting on the failure plane, and phi is the angle of internal friction. This shear strength, it's an inherent property of the soil mass. When normal load will act on the soil mass, automatically the soil, due to its shear strength behavior, it will give the resistance against this normal stress. So before failure of this mass, the shear stress will reach to the maximum level, that is called as the shear strength. In the field, during construction, when we found the foundation part or construct the foundation part, from this foundation the normal load, the normal stress act on the underlying soil. So on this soil, when the normal stress is acting, obviously the shear strength automatically will come in effect to resist the or to bear the normal stress, and the maximum amount of shear strength will be given by this equation C plus sigma f tan into tan phi, where this C and sigma phi, that is the property of internal property of soil mass, cohesion and internal frictional angle, and tau f, that is your normal stress that is coming from the foundation. Now this failure criteria can be expressed in terms of relationship between principal stresses, that is sigma 1 and sigma 3, and it can be rearranged in this form. So after rearrangement, sigma 1 becoming sigma 3 into 1 plus sin phi by 1 minus sin phi plus 2c root over of 1 plus sin phi by 1 minus sin phi, where 1 plus sin phi by 1 minus sin phi is equal to tan square pi by 4 plus phi by 2. Now coming about how we can determine the shear strength of soil. In laboratory, in these methods, we can find out the shear strength of soil. First one is direct shear test, second one triaxial test, then unconfined compression test, and the vane shear test. Out of these four tests, the first three one, that is direct shear, triaxial and unconfined, that is the laboratory method. Vane shear test is the field method or the in situ method, because in this test there are some limitations that we will discuss later on. We have to bring the vane shear test apparatus to the field, and there we have to conduct the experiment to find out the shear strength of soil. First, coming about the direct shear test. On this direct shear test, you can see there is a box in which the soil sample will be taken, and there are upper half and lower half portion. So here we will apply a direct shear force on the upper half. So due to the shear strength property, the lower half will try to slide over. So we can find out the direct shear, the shear stress amount. Before the shear stress, we have to apply a normal load on it. So we will applying the sigma, and we are finding out the tau, that how much it is resisting. Because on the left hand side, the lower half, how much it is resisting, that we will be measuring. So this is a typical normal stress and shear stress curve, will be plotted on a ordinary graph paper. Normal stress along x-axis and shear stress along y-axis. So the sigma tau value will be plotted, and it will be joined by a straight line. So the intercept along a y-axis will give you the cohesion C, and the inclination of this line, failure line, will give you the internal frictional angle phi. So if we take cohesion less soil like sand, that time this failure line will pass through the origin, because there will be no cohesion, only we are getting phi in case of cohesion less soil, that is sandy soil. But in case of C phi soil, we will get C value along y-axis, the intercept along y-axis, and phi value, the inclination of this failure line. Now coming about the triaxial test, is the most useful one. So from the name you can understand, tri-axis means we have to apply the stress on the soil mass in three directions. That is like this one. Here the soil sample will put inside a triaxial cell, and this cell will be filled with water. Then through water, a confining pressure, that is called as the cell pressure, will be transferred on the soil mass. So sigma 3 will act as the confining pressure in all direction of soil mass, laterally as well as axially. Then we have to apply the deviator stress or the additional axial stress till failure. that will give only in the axial direction. We have to apply this deviator stress till failure. So from this test, after getting the values of sigma and tau, sorry, not tau, sigma 1 and sigma 3, major principal stress and the minor principal stress. In axial direction, we are applying deviator stress, which is represented by sigma 1 minus sigma 3, and along lateral direction there will be our sigma 3 only, that is cell pressure or confining pressure. So from these values we will find out sigma 1 and sigma 3, and we have to plot the Morse circle. Then we have to find out cohesion C and phi value. Now there are three types of triaxial test depending upon the drainage conditions: UU, unconsolidated undrained test; CU, consolidated undrained; and CD, that is consolidated drain test. So depending upon the drainage condition, these classification are being done. Then it is our unconfined compression test. So from the name you can understand there will be no confinement. That means in triaxial test we are supporting the soil mass or the soil sample in all around by water. In unconfined compression test there will be no sigma 3. That means no lateral stress, only axial stress will be applied. So there will be no sigma 3, only sigma 1 is there. So if we plot it, it is like this, because sigma 3 is 0 and we are getting sigma 1 till failure. So we have to draw the Morse circle. Intercept along x-axis will give you the cohesion C, and basically these experiments are being performed for purely cohesive soil, because we have to place the soil sample, cylindrical soil sample, without lateral support. So whenever the soil mass will be made of pure clay, then it can be placed without any lateral support. So phi will be equal to 0. For purely clay soil, we will get phi is equal to 0. Next, lastly coming as Vane shear test. Previously I have told you that there is some limitation of this test, that this is a field test or in situ test where soil is very soft. Because for the other three methods that we have discussed earlier, to conduct these three tests, we have to bring our soil sample from the field to laboratory to conduct the experiment. But if the soil sample is so soft that we cannot collect from the field, that time the Vane shear test will be performed at the field itself. We have to bring our Vane shear apparatus to the field, and there we have to conduct the experiment. So there is a vane blade which will rotate. For this rotation we have to apply a torque at the top. So how much the resistance are given by the vane blade, from this expression we will find out the shear strength or the undrained strength or undrained cohesion of the soil. So this is all about this shear strength. Thank you.